Let's talk about serial jobs. Each serial job uses a single CPU, and therefore they are the easiest and most efficient to schedule. A lot of computational workflows assume many similar calculations, and these you can actually run in parallel, launching multiple serial jobs. This is what we call serial farming. We assume that all these jobs are independent of each other. You are doing things like exploring the parameter space, or running lots of similar Monte Carlo simulations, and all of this can be done with single-core serial jobs. A serial job can be launched by specifying number of tasks --n tasks equal to 1 flag to as-batch. But this is actually the default, so you don't have to specify it. If you don't specify the number of tasks or cores or processes, then the default is 1, and Slurm will schedule a serial job for you. Here's how you submit a serial job in Slurm. Assuming that you already compiled the code, you have an executable, let's call it serial, you will say as-batch followed by the job submission script. So the job submission script is shown here on this slide. It is a bash script. As you can see from the first line, we have the usual bash shebang telling the operating system that what follows is a bash script. And then we have 3 lines starting with hashtag or number sign as-batch followed by Slurm flags. So the first one sets the maximum runtime, 5 minutes. The format here is hours, minutes, and seconds. 5-minute maximum runtime means that once our job starts running and it runs for 5 minutes, it will get killed if it doesn't finish before then. So this is really a hard limit. It is enforced. The next flag simply sets the name of the job in the queue. And this is useful if you're submitting a lot of jobs, then you can actually give them unique names so you can distinguish them in the queue. The next flag is very important because it sets memory. So the default, if you just specify the number without any letters, it is assumed in megabytes. And here we have 100 megabytes, which is a very small number for a typical job. Remember that a typical node on Cedar would have 32 cores and 128 gigabytes of memory. That means effectively roughly 4 gigabytes of memory per core, right? So this is 40 times smaller, this example here, which is really a small amount. And you probably want to increase it to something bigger. If you forget to specify memory, then some small amount will be assumed. And this amount is dependent on the cluster, but it's something like 200 or 300 megabytes. So it's very small, and it's very good not to forget to specify this flag, because otherwise you'll be giving only very little memory. And similar to runtime, the maximum memory flag is a limit. So that means that once your job starts using more memory than you asked for, it will get killed. Okay, so these 3 are the as-batch flags that will be passed to the job. And then finally we have the executable, the command that we're actually running, and we're running our compiled code serial. Sometimes you might find that on production clusters you also need to specify your account by saying -- account equal to. And this could be important if you have multiple allocations. So this account is not your username, it's an allocation. Many of our users have multiple allocations. For example, they have access to the default queues, Rapid Access Service, RAS queues, and also they have access to a rack reservation through their research group. And in this case, we need to know which allocation you want to bill your job to. So you have to specify either the RAS allocation or the rack allocation. And if you forget to specify -- account, and again, this is only for production systems, so this does not apply to the training Cassiopeia cluster. On production system, if you forget to specify the allocation with -- account, and if you have access to multiple allocations, then when you use as-batch, this command will give you an error saying that you forgot to specify an allocation, these are the allocations you have, please use -- account with one of them. And then sometimes you might have a reservation. So typically we use reservations for workshops and summer schools like this one when we don't have a training cluster. For this course, we have a training cluster, so we're not using a reservation. But if you have a reservation, this will be also one of the flags that you will pass to the job scheduler through an as-batch -- reservation flag. Let me show you a demonstration. Here I'm in the codes directory where we had all these files for calculating pi. So let me clean this directory. And then because we already have the make file, I can simply type make serial. And this will compile pi.c serial code into an executable called serial. And by the way, let me show you the modules I have loaded. Actually, I don't have a GCC module, so let me load the GCC module load GCC. And this replaces the default Intel module with the GCC module. And let me type make clean again. And then I'm going to say make serial. And this will compile using GCC version 5.4.0 that I just loaded a minute ago with the module load command. So here I compile my code with make serial, which simply ran this command, and now I have the executable serial. Now let's take a look at the job submission script. So it is job underscore serial.sh in the same directory, and I'm going to open it in Nano. I'm going to increase memory to 1000 megabytes because 100 megabytes is a very small number. And then I'm going to save this file. So here's the job submission script that I will use to submit my code. And you have to make sure that you have the serial executable. And then I'm going to say as bash followed by the job submission script name. And if it's successful, it will simply return the job ID, in this case, job number 5. And if I type SQ, that will show me all currently running jobs. If I type S, just 2 letters SQ, that will show me my running jobs. And as you can see, my job is currently the only one running the system. It has job ID 5, and it is asking for 1000 megabytes of memory. And I asked for 5 minutes. So now it's, as of the time of this command, it was 14 seconds into the run. State R means that it's currently running. Then you see the name quick test that I specify right here in this flag. And then you see that it's a serial job, so it uses a single core, single CPU, and a single node. Now I type SQ and it's finished running. So all output of a Slurm job will go into a file that is called Slurm dash, then the job ID, because my job had ID 5, so it should be Slurm 5 dot out. And this is the standard output from my serial code, which simply computes pi using 10 billion terms, and then also produces or shows the error in this calculation. One of the exercises we're going to do together later on is benchmarking the code for computing pi. It's the same mathematical algorithm. We're going to run two versions of this code. One was written in C, and the other was written in Python, using exactly the same mathematical formula. And then we're going to time this code. So what you can do here is you can either submit 2 different jobs, one for the C compiled code, one for Python, or you can actually submit a single job where you have 2 executable lines, and you will run in each line the corresponding code. Another topic that I want to talk about very briefly is array jobs. An array job is a very useful tool for submitting many serial jobs that have the same executable and have very similar parameters. They usually only differ by the input they are receiving through a file. So a job array is very useful if you're doing Monte Carlo, lots of Monte Carlo simulations and essentially running the same code but just many times, or you're exploring the parameter space and you're passing some input data to the same executable, and this input data varies from one computational run to another, but the executable stays the same. So the idea of a job array is, for the scheduler, it is much simpler to process a job array than to process multiple serial jobs. And this is primarily why we use them. So here's an example of the job submission script. In this case, as you can see, it's a bash script. And when we're submitting an array job, so this array will result in 30 individual jobs indexed from 1 to 30. And then here I'm specifying the name. So it's a single job name for the entire array. Each job is going to have the maximum runtime of 2 hours. And in this case, 100 megabytes of memory. The output of each job will go into its own file. So this will launch 30 jobs. Uppercase A is replaced by the job ID, and lowercase a is replaced with the array index. So that means that the output will go into the file myprog, then the job ID, for example, job number 6, and then we'll have a number from 1 to 30, .out. So all standard terminal output from my program will go into that file, and all standard error will go into a similar file, but with the .err extension. And then the program I'm running is called my program, and it takes the input file, input, then a number dot, and the number here is a number from 1 to 30. So this way, doing it this way actually lets you launch 30 computations, and each computation will take its own input. But for this to work, I actually have to prepare 30 input files named input1.dat, input2.dat, and so on, up to input30.dat. And each one of them will have some parameters for your calculation that my program will process. And this way you can actually launch 30 individual jobs through a single job submission script.